Hi, everyone. We have the great pleasure today to present Professor Mridul Nandi. Professor Nandi is a professor in the Applied Statistics Unit of the Indian Statistical Institute in Kolkata, India. Currently, he's the professor in charge of the Applied Statistics Division and acting head of the R.C. Bose Center for Cryptology and Security. His main research area is in symmetric cryptography. He's one of the best well-known researchers in this area, and lightweight cryptography also. And his research basically focuses on cryptographic algorithms and security analysis. He did all his bachelor, master's, and PhD in ISI, Kolkata. And then before joining Indian Statistical Institute, ISI, he was a postdoc fellow in the CICR of Guadalupe University, a scientist, a professor in the Computer Science Department of Civil Staff Mexico, and a guest researcher for the SHA-3 project in the National Institute of Standard and Technology, NIST, and also in the George Washington University, USA. So it is our great pleasure to present Professor Mridul Nandi in our seminar today. Mridul, the floor is yours. Thank you.
Thank you, Francisco. So it's very nice to see all of you. So I have known you for a long time, and also Raghav. So it's very nice to see you. So okay, so today actually it will be a little bit technical talk, but I will not go much detail, but definitely there will be some technical content, and I would like to prefer the whiteboard. I have not prepared any presentation, so I will try to go slow so that we can follow you. And if you have any questions, you can interrupt me in between. So it is you don't have to wait till end of the talk. So I'm fine if you stop me if you have any question. Okay, so my talk is about indefensibility. Is not only for the hash functions, it's also for ideal ciphers. So indefensibility for hash functions and for hash and block ciphers. So these are two important objects in cryptography, right? So hash and block ciphers we study very well, because in symmetric cryptography, these are the important building blocks. Right, so we use these to achieve several things. Okay, so what you have to understand, like what are the security notions we demand from the block cipher and hash functions. So hash function, as I hope you know, hash functions this is a function which takes any arbitrary message and returns some amount of bits, like say returns some. So this 0 1 star means any arbitrary bit to it, and returns. It can return like 256 bits or 512 bits or any fixed size bits, so that the output of the hash functions looks like random. Okay, this is the general notion of the hash function. So we try to compress the message into a random looking object, but we demand some additional features. What are the features we demand? We demand like a collision security. Collision security means we do not have two different messages such that the hash value should be equal. Actually, we will have, but the thing is that it will not be easy to get such collision pair. So the functions is not injective. That means that functions has a multiple inputs for same output, but it will be hard to find such an input pair actually. Okay. And another important notion is the pre-image resistance. Pre-image security, or sometimes we call one-way security. So it's like given the hash value, it will be hard to find any message such that the hash value is that particular value, that particular target. So these two security notions are kind of essential security notion for hash functions. So if you want to design hash function, you must achieve these two security. Okay. Okay, but there might be, in addition to that, there might be some other weakness. Like even if the hash function satisfies the collision security and pre-image security, you may not get the full security, like a random oracle or random model. Usually, random oracle model, we demand something higher, something super secure. Like If you have this security, then all these security like collision security, pre-image, and the second pre-image. There are several security notions. I am not going to discuss all those security notions, but all these will be like an immediate corollary, immediate implications from the random security, like random oracle security. So kind of strong security notions, which I am calling it pseudo-random oracle. Pseudo-random oracle security. This is like a strong security which will imply all these security notions you want to achieve. Okay, so what pseudo-random oracle means? It basically it means it's the output behaves like a random. As in the beginning I said, like the output of the hash function should behave like a random. Okay, if the output is definitely you cannot achieve completely random because there is no randomness in random source to generate a random output, but it's like a computational notions or cannot distinguish from random output behavior, right? So we use these hash function for sometimes to generate the pseudo-random bit also. Okay, so this behave like a random will be your like a goal, but the problem is how do you formalize these notions? So that is the crucial point, like how we can formalize that something behaves like a random. Okay, and similar thing happens for the block ciphers. So quickly I discuss what block cipher is. So you know, like block cipher has two input. Suppose I consider 128-bit block ciphers. Then we have a one input is a key, say key size is say k bit, and then we have a 128-bit input, that's a plain text, and returns a cipher text which is also 128. Okay, so this is a block cipher. That means like every k, it is like a permutation. It should be a permutation. Like there should be an inverse. Like ek is the permutation, means we have an inverse. Okay, and the block cipher, you know, like is a essential primitive or building block for design encryption algorithm, encryption or MAC or authenticated encryption. So it's a very useful block. So there are other similar notions like tweakable block ciphers. So these are also powerful, but the basic essential sense is the block cipher. Like you have for every key we have a good permutation. And here we want a security called like a PRP security. So the security we usually want PRP or SPRP. What it means? It means the pseudo-random permutations. So it behaves like a random permutations. Okay, but again they will be like a little more stronger security notions, like a pseudo-random oracle. We have like a ideal ciphers. So ideal ciphers will be something stronger, like pseudo-ideal cipher, you can say. So pseudo-ideal cipher, pseudo-random oracle, these are like a much stronger notions than the standard security notion like collision security or PRP, SPRP. Okay, so PRP, SPRP is like a standard model security notions, but the pseudo-random, pseudo-ideal cipher is the ideal model security. And for these two notions, like pseudo-random oracle and pseudo-ideal cipher, we need something called the indefensibility notions. So this is first introduced by Maurer in 2004, I think, 2004. He introduced this notion indefensibility. Okay. Okay, so just a few things to mention. What are the things that pseudo-random oracle or pseudo-ideal cipher captures what was not captured by the hash function, like collision security or PRP, SPRP? Like what extra it is giving? Definitely, we understand the randomness, but can you say in a very layman way, like, okay, can we have some nice property that is captured by this indefensible notions? So I will give two examples for hash functions, one example, and for block cipher, one example. For let us first tell the block cipher example, because this is a very simple example. This is a simple example which it will be easy to explain that. You know that DES. So you remember the DES is one of the oldest block ciphers, Okay, and it has been used long time back, but nowadays we don't use much DAS. So DAS is replaced by the AES, NIST recommended NIST standard block cipher AES. But before it was DAS, which was more popular. But there is a property in the DAS block cipher. If you know, I don't know that you know or not. It's called the key complementary property, or key complementation property, or key complementary. Say, what is that? That is like if you encrypt DAS by some key K, okay, and if you encrypt a message M by some key K, and if you encrypt the same, so the complement message M bar by the K bar, okay, so M bar means you just bitwise complement, you just convert the 0 to 1 and 1 to 0, okay. So if you use the bitwise complement key K bar and the bitwise complement message M bar and encrypt, then you get almost the same thing again, bitwise complement. Like this bitwise complement will be, so whatever the hypertext, you take the bitwise complement, you get that, right? So you got a nice relationship between two encryptions. One encryption is done by K and the other is done by K bar. Okay, that relations you cannot capture directly by the PRP or SPRP notions, but that relation will be captured by the indefensibility notions or the pseudo ideal cipher notions. Okay, so this is one example. Another example, if you recall, one simple block cipher based hash function, or not a hash function, it's a compression function. So the compression function is actually hash function, but the domain is not like an arbitrary bit. Like when you design a hash functions, what we do, we first design a compression function, okay, where the input size of the compression function is fixed, say 512 bit to 256 bit, okay, and then use that compression function in a certain ways. We call it mode, the hash mode, or to design hash function, we call it hash mode. It's the same principle for design MAC or other encryptions. So you use the internal primitive several times to get your bigger domain function. In case of the hash functions, you take any arbitrary message, you use the compression function, right? So there's one popular way to design a compression function, which is called Davis-Meyer. So what Davis-Meyer compression function does, it takes a block cipher E, okay, and then it takes a key. Suppose key is 128 bit. You just take AES, okay. So K is take 128 bit, and you have a message 128 bit, and you XOR this message. You XOR the input, right? So in pictorially, it looks like that. Like you have a EK, the M goes into the block cipher, and then whatever the output ciphertext, you XOR it. Okay. So the compression function is actually takes two input. So my compression function F, it takes K and M, and it returns this. Okay. So 256 bit input in case of AES, and returns 128 bit. Okay. So it's a compression function. It looks good. If the E is good, then compression function has no issue. In fact, you can prove that it has a collision security, pre-image security, all the securities are there. But still, it has certain features, some features which may not be desirable. Maybe some features, for example, key complementary property. Like one may think that, okay, what is the problem with that? Means I am fine with that. Or maybe the property I'm going to tell for the Davis-Meyer, you may want someone may be fine with that. But you never know. I mean, some applications you probably do not need that particular property. Property means here I am saying in the bad sense, in the weak sense. If you have some features, if you have some property for your constructions, it's not desirable for random things. Random should not have any pattern and any property, any features, right? It should be random. Like any feature should have very low probability. So this is any features or pattern should not be there. So what is the property you can get it from the Davis-Meyer? if you look at, if you take the inverse of the block ciphers, say EK inverse of 0, you get something, say called M0. Now, if we compute the Davis-Meyer encryption, Davis-Meyer compression function for M0, what do you get? So this will be 0. So you XOR M0, so you get M0 back, right? So the input will be KM0, output will be same M0. So if you ignore the K, this K can be anything. It's like a fixed point. So we call this as fixed point, right? So the fixed point features is not desired for ideal cipher. For compression function. Here it's not ideal cipher. Here you are designing the compression function. So fixed point property is not good for compression function. Probably you can exploit that fixed point for some weakness, for some other attack. Okay. So these are the properties. Those are not captured by the collision security or the second pre-image or pre-image security, but will be captured by the pseudo-random oracle or pseudo-ideal ciphers. Okay. So that's the motivations, like why you should consider the indefensible security notion. So I hope you have this motivation. So you have any questions, you can ask me, and then I will go to some more concrete examples and study. And next I will discuss what is the definitions of these indefensible security notions. And the definition is very strong, and because of that, we will see that some algorithms are easy to break in that definitions. But that is the natural definitions as Mora given, and in fact the definitions is kind of important for application point of view. Like if you want to use that random oracle in appropriate way, then you have to take that as definition. So I'm going to tell that, but I just take a little bit pause. So if you have any questions, you can ask me, because the motivations point of view, I have described some examples. So are you fine? So okay, so
yes, Mridul. So far, no questions. Oh, let me see. There is one.
Yeah, what I just missed the message.
Yes, there is a question right now.
Yes, but can you read that? Because this
yes,
message
yes, absolutely. Yes, absolutely. It says, in case we replace EK by a public permutation in Davis-Meyer, how the oracles will change?
In case we replace EK by public permutations.
Yeah.
Yeah, then we still have the Davis fixed point property, right? Because if you take the inverse of 0, the P inverse of 0. So if the EK EK actually is a permutation. So if it is P and you take the P inverse of 0, then you get the same feature. So it will not be a CQ. So the same features will be there.
Okay, thank you. That question was asked by Raghvendra Rohit.
Yeah. Okay. So now I move to the next page, like where I'm trying to define what indefensible security notions, like how do you define the indefensible security notion? So collision, pre-image, these are very easy to define. Like this natural definition, like you don't get collisions. It's hard to get collisions, but how do you define indefensibility? Like it's like a pseudo-random oracle. I use two terms. I call pseudo-random cipher, pseudo-random oracle, and pseudo-ideal ciphers, right? Okay, so basically they are indefensible in security, but the object is for either for hash function or for the block cipher. That's why I have given two names. Okay, so the definitions for indefensibility is basically a distinguishing game. You cannot distinguish two objects. Okay, so the indistinguishing notion is the notions we use for the standard model, like when you define the pseudo-random permutations, or even when you define the public key encryptions, when you define the in-CPA security, we use the indistinguishing notions. Like adversary cannot distinguish whether the ciphertext is encrypted by the first message or the second message, right? So this type of indistinguishing notions is used in many cases, even for the public key in symmetric key. And we consider an appropriate type of indistinguishing notions when you define the indefensibility. Okay, so when you have indistinguishing notions, we actually have two different possibilities, two different worlds, and you have to tell like which one is that. Means you don't know, well, one of that was considered, and we get the output, and that will be given to the U means the adversary, and the adversary has to tell which one it is. Like in artificial intelligence, like we say that, okay, the human and computer, like they are indistinguishable. Like those who believe the AI, like then you can replace human by computer, then okay, any human or any adversary cannot distinguish human and computer. So the human and computer are like two objects, two worlds, and you cannot distinguish. Same thing here, like you have two worlds. Okay, so here the hash functions, when you study some hash function, let's consider in terms of the hash function. Let's look at the definition in terms of the hash function, and then we come to the similar definition for the ideal block ciphers. So for hash function, what like we have a hash function, say H, it uses some compression functions. As I said, like some small f, like compression functions, like if you see the Markov-Damgard, quickly, if you recall the Markov-Damgard, like we have a f which takes some input, say we start with the initial value and takes M1, and if M1 is your message, then you are done. If M1 is not your message, you have more message, then you take next part M2 and you continue like that. So you get the hash output of the F. It's not a hash output, we call it intermediate chaining, and we continue this until you finish all of your message. Suppose M4 your last block and you are done, and you get the hash value, final hash value. Right? This is a Markov-Damgard. So this is a Markov-Damgard hash function which uses F. So H uses F. Okay. So what algorithm or what adversary can have? The adversary has a description of F. So adversary, whenever required, it can compute the input output of F. Right. So you can make queries to F as a black box ways and get the output. Okay. And also adversary can make query to hash function H. Okay, so here like the total hash output, like you can give the message for the Markov-Damgard hash functions, like you can give the 4 message M1, M2, M3, M4, and you get the hash value. You don't get the internal values. Or you can ask F also, means you can ask just what is the output of IV and M1. Then it will say, okay, the output is H1. And then you can ask, what? Okay, tell me what is the output of F output of H1, M2. Then it will say H2, and so on. You can get all these internal values. But if you ask your H, okay, what is the output of M1, M2, M3, M4? You don't get H1, H2, H3. You get hash, that output, the final output. But because the capital H actually returns the complete thing. It computes everything, right? Okay, so this is the these are two oracle you have. You can either take the help of the small f, and you can take take the help of the capital H. Right? What we want, we assume that f is good. F is like a random oracle, means there is no. So whenever I give a distinct input, the output behaves like a randoms. But here, basically, I am assuming a random oracle of F, and I am trying to define the random oracle for H. So basically, indefensibility, what I want to mean that to define the random oracle for bigger things for H, not for the F. We assume that F is good, okay, but H, some design, something is internal picture of H is given. You may not be sure that whether this H is good, okay. So for example, that we call the block cipher things, like the block cipher may be good, but after doing the Davis-Mayer, you are not sure that whether Davis-Mayer is good compression function or not. And you see that there is a pattern, like okay, you see that fixed point of Davis-Mayer, right? Similarly, I want to see like whether Markov-Damgard is good or not. So what adversary will do, adversary will try to distinguish this world with another world, the similar world, where you have a big random oracle. So what random oracle means? The random oracle basically, it takes, whenever you give a distinct message, a distinct input, it will return a random output. Okay. If you give the same input, then it will give the same output. But if you give it can be distinct by 1 bit or anywhere. So if you give a different input, it gives a random response. So that's a random oracle. Okay. So it's a big random oracle, and this F you can assume like a small random oracle. So small and big, what is the difference? The statistical point of view, they have no difference. Only thing, the input size. The small random oracle, the F, the input size will be like say a few bits, like 512 bits. But the big random oracle is the hash functions. Is a replacement of the hash function. It's not a hash. You do not know that, but the hash function is behave like a random oracle or not. That's the part of the definition. But if it is behave like ideal object of the hash function will be a big random oracle which can take arbitrary size input. Okay, so this is the big arrow, and it takes so it can adversary if can access of this big random oracle. Okay, and should not be able to distinguish these two worlds. But there is a problem, like we have two hands of the adversary in the left hand side, but there is only one hand in right hand side, right? It means adversary has two oracles in one world and one oracle in the other world. That's clear that it's not, you cannot compare, right? Definitely adversary will understand that which world it's interacting. So I have to give something. I have to give something here. Okay, so this something is important, and that's called simulator. Okay, and simulator will have access of the big random oracle. Okay, yeah. So so now you see the arrow indication. The arrow represents that who can make queries to whom. Like here, like hash functions, you can see like that hash function can make query to this functions, and the simulator can make query to random oracle. So opposite directions, right? Because random oracle is a standalone object. It doesn't need help of anything. Random oracle will return randomly. Okay. Hash function on the other end requires the help of the small f. Hash functions will make the queries to small f, and then it gets response and so on, right? So if you cannot distinguish, then I will say the hash function is good, means pseudo-random oracle. So definition of hash function, the H is called PRO, means pseudo-random oracle. If A cannot distinguish above two world.
Mridul, we have a question here.
Oh, okay. Yeah. Can you tell me?
The question is, does the notion of indistinguishability apply also for cryptographic permutations, for example, like Keshak?
Yeah. So no, for the primitives, we do not usually apply, but for the modes we apply. Like for the Kechak permutations, we assume this is good permutations, is the ideal permutations, but the Kechak hash functions is definitely applicable. Like we can have a Kechak hash, which uses the Kechak permutations. And we expect the Kechak hash would behave like a random oracle, and there will be a simulator. So these two games should be indistinguishable. Okay, so this Kechak was just an example of the hash functions. It can be any hash function. This H can be any hash function. Okay, so Kechak, if you see that Kechak is actually sponge hash function, and it is proved already that sponge is indefensible. Actually, there is a proof that for sponge actually is indefensible. So in this case, you cannot distinguish. But if you take the Markov-Damgard hash function, this one, then it is not indefensible. Unfortunately, Markov-Damgard hash function is not indefensible. That means there is some certain features the Markov-Damgard has that we should not expect from the random oracle, and that features is exploited to make a distinguishing attack, to have a distinguishing between these two worlds. And if you know something, probably you know this, but I just saying once more. This is very, very in the beginning we study this, like length extension attack in cryptography, or even if you study the handbook of applied cryptography, you see that length extension attack is also written somewhere. It's in the beginning of the book, or it's very, very, very useful notions. Length extension attack. Okay. That property is there for the Markov-Damgard hash function. So, what is length extension attack? I will describe length extension attack for the Markov-Damgard hash functions, but it's actually it's kind of a general notions. You can use this length extension attack for many other cases. Whenever you have certain lengths involved, like it's not just one block, two block message. It's whenever you have a something, the input size can be large enough, then you can have this type of notion. Okay, so what is length estimation attack? Okay, for the market vanguard, if you see, if this is the hash output H for M1, M2, M3, M4, then what you will see that if you take one more block, M5, and you compute F, you get H prime, right? So okay, so here what is happening here, like you have a hash output H, which is the market vanguard hash output, okay, for the M1, M2, M3, M4. Now if you add one more block, so you are extending the length, then you get H prime. Okay, so this type of things, like you have a two messages basically. One message is M, which is in this example M1, M2, M4, and another message is a little bit bigger than M. So M and M5 here. Okay, so M and M5. So what you can do from the hash value of M, it is true for the market vanguard, not for sponge. You can compute, and also using M5, you can compute hash of M, M5. You don't need to know the M. You only know the hash value of the M. You don't know the M, the M1, M2, M3, M4. You only know the hash value of M, and you know one more block, M5. Then you can compute the hash value of the total message, M and M5, without knowing M. Okay, so this is you can, if you know the sponge hash function, you can check the length estimation attack. You will see that it's not applicable. You cannot apply this type of things for the sponge, because there is a in the sponge there is a capacity, like there's a something in bottom, like which is not revealed, which is not a part of the hash value, because you do not know that capacity part. That's why you cannot compute the bigger hash message output. So that's why the length estimation attack is not applicable to sponge, but it doesn't say that the sponge will be indefensible. So sponge is indefensible. You have to prove it mathematically, but there's some type of attacks, you know, and if you see that those attacks are not applicable, then it looks like, okay, it might be indefensible. Okay, but you have to give a proof. You do not know, there might be some other features, right, which can be exploited. Okay, so this is one important example I want to tell, that market vanguard hash function is not indefensible.
Mridul, one quick question that we have here. What about the simulator? How does it look like, mathematically speaking? The simulator.
Okay, so, the simulator. Yeah, so simulator. What simulator will do actually? So simulator, it should behave like a F. So if you see these two worlds, like one world is H and F, and the other world is random oracle and simulator, right? So the order matters actually. The left hand side you have a H, and H and RO should behave similar. Okay, this is one thing. Definitely you should have this, because that is the reason. If you cannot distinguish, that means H behaves like a RO and F behaves like a simulator. Actually, you should say other way. The simulator behave like a F, because F is already there. F is already there. F, RO, they are already there. F doesn't depend on simulator. Simulator you define after looking at the designs, and you choose your simulator such that it behaves like F, and F is already random oracle. So simulator should behave like a random oracle. But simulator should maintain the relationship between the H and F. Means simulator, you must try to define, if you want to prove the security, simulator should be like that, like H of random oracle of simulator. What I should say, like H of simulator should behave like a random oracle. Where simulator, so if you have a market vanguard hash function, say market vanguard hash functions use market vanguard hash use F. In case you could prove that market vanguard hash is indefensible, you must design some simulator, okay, such that the market vanguard hash of the simulator should behave like a random oracle. Already there is random oracle. So what it means, like you have a random oracle. Okay, so that random oracle doesn't follow the market design. Random oracle is standalone random object. Okay, you are trying to fill up something by simulator such that market with simulator behaves like a random oracle. If you can fill up this, then we can say that it's good. For market it's not possible. For sponge is possible. Say sponge of simulator will behave like a random oracle. So simulator basically is some object which is filling up the this relation. Like sponge of what is random oracle? Sponge of you have to define certain object. Like if the response of the simulator should and if you consider the response as like a sponge permutation, and then you apply the sponge, then you should get the exactly same response like what random oracle does. So you have to do kind of back calculations. Simulator is basically doing the back calculations to make the compatibility of the hash function. So simulator mathematically it's an object-wise it's algorithm. It's an algorithm which should give a response to the adversary query. So adversary will make a query. The query will be similar to the query to F. Like what is the query for F? Like here, say if the IV is say 128 bit and the M1 is 128 bit, so 256 bit. So the inputs to F is a 256 bit. Same will be for simulator. So simulator will receive 256 bit input, and it try to respond like F, but not just following F blindly, because he has to maintain that random oracle should be of eventually the final hash output. Okay, so that relation has to maintain. So this is the important goal of simulator when you design this. So compatibility, maintaining the compatibility, because you know that at the end it should be like a random oracle output. You can respond H1 here randomly, H2 here randomly, H3 here randomly, but here it should not return H randomly, because this H should be the hash output of the M1, M2, M3, M4. Okay. But what happens, like H1 you also cannot return randomly, because if the M1 is the message for the capital H, then whatever the hash value, that should be H1. So like that, like you have to maintain the compatibility with the random oracle. Okay. So this is the defining simulator is a little bit complex when you want to prove security. On the other hand, for understanding attack might be easier, because in that case you see some certain features, and those features are not should not be desirable in ideal world or random world. That's why the understanding features will be easier. So let us see one more features for other design. Like let's consider the say you know the triple days, right? Triple days or double days. Okay, so triple days, we have a 2-3 block ciphers. Okay, so the motivation for triple days was to increase the key size, because the key size was small and this is not large enough to protect against that exhaustive attack. So how we can increase the key size? Okay, why not you have say 2 or 3 keys, and then you apply the block cipher days several times. So suppose you have a two keys, but I repeat 1 keys. So EK1, EK2, and then again EK1. Okay, so that means you have some message M, and then you come here and you get cipher text. So you apply the 3 block ciphers. First one by you use a K1 key, and then you use K2, and then again you use K1. Okay. So this you can imagine like it's like a big block ciphers E, or maybe you call it this a small e, like a compression function is like they are like a small e, and this one the capital E, which is a big hash function or ideal block ciphers, but it has 2 keys, K1 and K2. But the plain text size is here same. It doesn't expand the plain text. The plain text remains same, like a 128 or whatever the DS out plain text size. But the key size is increased. Key size is now double, K1, K2. Okay. Now the question is it a good ideal cipher? It's considered to be a good block cipher, because if the small e is good, then it is also good. But the problem is that it's you can see that it's not also good. You have certain features here. Okay, that features is not easy to identify quickly, but there are certain features. Okay, so for example, the features is I'm just trying to trying to explain this feature. Maybe then you can ask some more question and you can stop. So like you have EK1. Okay, so you take one value, because you remember the block cipher, you can have inverse. So if you want, you can take the inverse call. That's also powerful. Like you see for the fixed point, Davis map. You take the inverse of 0 and then you get a nice feature. So this inverse is powerful, and because of the inverse, proving securities also sometimes becomes very complex. If you don't have the inverse, then it's easy to prove. But if you have inverse, then proof is difficult. But because the attacker has a two-way, attacker can move, can make forward query and then backward query and then forward query. So sequence of the queries can be arbitrarily adaptive by forward and backward. So it becomes more complex. So what attacker will do here, like attacker will first choose, say, one message, say M. Okay, so what I will make some convention here. What I will do here, I will draw in certain different ways so that it will be easier for you. Like here, like EK M equal to, say, M1 equal to, say, X1. I will write, instead of drawing this, I will write M1 to X1 with label K. So edge. So this is like edge from M1 to X1 with label K. Okay. So the edge label means represent the key, and the left-hand side is the input of the block cipher, and right-hand side will be the output of the block cipher. So when you compute, basically, first you have 3 edges. Say if you have X1 and then X2, this is X1, this is X2, and then you have a C, right? And the label will be like you have a K1, K2, and K1. That's a complete computations, right? You get from M to C by these internal computations. That's a better way to represent. Then you can easily, instead of drawing the block cipher square, you just represent through graph. Like you have an edge and keys. Okay. So what you will do here, like you have a message M1. Okay, sorry, you start with some X1 and you make the inverse query with some K1, you get M1. Okay. And then okay, and then you use another key, K1 prime, you get M1 prime. Okay. Now, if you use K2, sometime to first draw the figures, so then probably you will, and then you have a K1 that can be like a C1 and K1 prime, it will be C2. Sorry, C1 prime maybe. So let me write this K2 on top so that it's uniform. Okay, so what it says that the adversary can, because adversary has the access of this small one, like small block ciphers, right? It has 2 oracles, like one is a big, one is small. Here, small is the small e, like this one is the small one, and the big one is the eventually you do apply some mode and you get some block ciphers, capital E block ciphers. Okay, so here, like you can start from here, the X1, you can compute capital M1 and M1 prime. Okay, and then if you apply the block ciphers call with the K1, K2, you get some C1. Similarly, you apply block cipher call with K1 prime, K2 prime. Sorry, K1 prime and K2, same K2. Then you get C1 prime. So this calculations simulator cannot see. So if I quickly move to the previous page, where to the previous page? Oh, okay. So if you see here, like here, you make some queries to random oracle, right? So that queries, you cannot, so when adversary makes queries to random oracle, simulator cannot know what are the queries the adversary is making. So this is one point I didn't mention. It's a very important point, and that makes further difficult to prove something secure. So all the queries here, simulator cannot see that. There is a one notion called public indefensibility. This is classical indefensibility. The one important notion is public indefensibility. In the public indefensibility, simulator is allowed to see all the responses. It's like a public, all the query responses are public. But the classical indefensibility, you cannot have any knowledge on this query. So whatever queries here you make, this query means from M1 you compute C1 by making the big capital E calls that you do not know. Simulator doesn't know. That means simulator does not know the K2. K1 may know because already it computes, but the adversary computes M1 through K1 by making inverse query, and K1 prime by making inverse query it obtains M1 prime. So K1 prime adversary knows, but adversary does not know K2. Okay, so adversary does not know whether C1 and C1 prime actually computes through K1 K2 and K1 prime K2 for some K2. Now, if adversary is asked simulator, okay, what is the response? So what is the response for C1? C1 is again a backward query. K1. So C1 is there. What will be the response? And EK1 prime and C1 prime. What will be the response? This response should be equal. In real world means the left hand side, the response should be x2. Some value should be equal, right? But the simulator will not know whether the response will be equal or not. Simulator cannot tell that whether I should give a same response or not. So this is a little bit tricky observations. May not be clear like why this is some features here. Like the features are coming because of this. It's not the feature for just for the only block cipher. It's a combinations of the block cipher, the complete block ciphers, the big E and the small e also. Like you have a same point here. So I have I have making two computations. One is using K1, K2, and another using K1 prime K2. There are two keys. I should go to the random cipher C1 and C1 prime. They should not have any relation practically, but they are actually having certain relations, because if you go inverse, just one step back, you come back to same x2. They have certain equalities. That should not be there for ideal cipher, and that property is actually used to distinguish the cascade ciphers. Okay, so the fact it becomes that a triple dash with two keys is not ideal cipher or pseudo ideal cipher. So you see, there are several popular objects which we use, like a market number hash function, or maybe the triple dash, triple encryptions. They have been used for different contexts. But if you want to achieve the strong security notions, the randomness security notions, the indefensibility notions, then they fail to achieve that. Okay, so this is so then now what one can do, like as a designer point of view, you can ignore this security notion because it's too strong. It's actually too strong. Means when even if you prove the security, you don't get good bound. The bound for security usually is a little bit weak as bound. Okay, so because this definition is too strong, you give a more power to the adversary. You can ignore these definitions, but if you can prove that there is no loss, right? If you can prove some designs are good, that means at least you are sure that these designs cannot have any features which might be weird or for maybe useful for some applications or some scenario, right? So you are like you have like a protection. Okay, means you are safe as long as your small f or the small e, the block ciphers is good. Whatever you are using at the end, like triple dash or the market number is not secure, the sponge will be your good hash functions, right? So and one more thing, that whatever security you prove from this particular notions, strong notions, all the security notions like collision security, pre-image security, or PRP, SPRP, those will be, you will get at least that much security, maybe more. You don't know. Means maybe because of the security is strong, you are bound, or security strength may be less. And if you want to prove that pre-image security, you may get a better security. Usually pre-image security, you get a full 128 bits. If the hash output is 128 bit, then you expect 128 bit security. But when you want to prove that as a pseudo-random oracle, you get 64 bit security maybe. Okay, you don't get more than 64 bit because of the collision is 64 bit, right? So if you prove 64 bit security, then you can say that, okay, the collision ratio is also 64 bit security, pre-image is also 64 bit security, but you may expect better security in pre-image, that you have to have a separate proof. But you have like one common guarantee for many notions. After proving the indefensible notions, you have a common guarantee. Like, okay, you have at least this much security for all security notions you want to achieve. But what the problem, the downside is, it's not easy to prove, or sometimes you cannot prove because it's broken. And now it's your choice, like whether you really care these notions or not. That will be the designer's choice. If it feels that, okay, I am not paying much in terms of the efficiency point of view, like a sponge, okay, their performing is good, like as good as like a macadam guard. So then let's use sponge because it's indefensible. You have additional protections, right? So that principle one can use. But if you see that, okay, to achieve the indefensibility, I am paying a lot, then probably you can ignore that performance versus the security trade-off. Like, okay, let's ignore the super security and stick with some standalone security like collision, pre-image, pseudo PRP, SPRP, those standalone security notions. Okay, I think I am done with mostly I'm done. So you can ask some more questions so that I can take up and like I can continue. So I am done. Thank you.
Thank you, Mridul, for your presentation. We have some questions. One question that was asked is, how far are we from doing all this sort of analysis using automatic tools?
Okay, so for not for the even for the indefensibility, for the standalone security also, like PRP, PRF, we are actually far away. So eventually the automated tools can guarantee certain proofs. So what you write a proof, you give that proof to automated tools, and automated tools can check whether the proof is correct or not. This is one thing. The other thing is the automated tool can give, after you give a designs, automated tool may try to exploit different structural pattern and if they can identify certain pattern or not. Okay, so I know there are certain things like is done for the indefensibility actually, like there are certain designs of indefensibility. Say if you look at the 5 round of Dubidakov, it's not secure. There's attack. So if you give the description of the 5 round Dubidakov and the automated tool can describe the attack. Okay, so I don't think that automated tool will give a proof by itself. It will be a kind of, to me, it's like a dream. We cannot. It's not possible, I think. But if you give a proof in certain format, automated tool can tell that, okay, the proof is correct. This is one direction. The other direction, automated tool can search for some attack, some pattern, and that I know actually there are some. If you give some small design, automated tool can give some attack on indefensibility attack. Okay, so there are certain tools which can find out the pattern, which can tell your proof is correct or not. So these two directions, like proving point of view and the attacking point of view. Yeah. But definitely, automated tool cannot give a proof that is secure. It can identify some attacks. It may miss some attack also.
Okay. Okay. Thank you, Mridul. We have one question from one of our young researchers. He's asking you, you are one of the best known experts in breaking schemes. How do you do that? It's a very open question, but maybe you can share with us.
No, actually, no. So there are breaking schemes means there are two things. I must tell. So One is the cryptanalysis. I am not good cryptanalysis, I must say that. The cryptanalysis is you have to know the primitive, you have to see the designs, like you have, there are lots of cryptanalysis tools. The other thing is the breaking scheme in terms of the design point, the modes point of view, like the market modes and say sponge mode. And what happens that you have to prove the modes are secure. Like proving means like one type of proof will be proving indefensibility, say. Okay, you have to give a proof for indefensibility that this mode is indefensible secure. Okay, so people make mistakes, or sometimes people don't give a proof and they propose that modes, or there's some modes available, maybe the proof is not complete. Or so if you understand the modes and if you understand how we prove, then if you read some proof, then you may find some weakness or some gap in the proof. Like so when I see some proof, I find that, okay, this proof looks like it's not complete, it's missing something, it's jumping, to make some conclusion. And then I try to see what is the gap, and then I try to exploit that gap to make such attack if possible. There might be two possibilities: either the actually is good, secure, but the designers didn't write the complete proof, makes a big jump and just make a conclusion, and then you may have one may have a detailed proof for that. Okay, so it's filling the gaps. The other is actually there is no, you cannot fill the gap. It's actually it's not correct. The statement is not correct. Then you have to understand the where is the weakness, and then you try to attack. So here I need to make one point. What I usually do when I have some mode and design, I try to do a to and fro approach, like both direction approach. So when I have mode, I first try to attack. Okay, and then I see, look, what are the possible attacks on the mode, and if I don't get it, then okay, then I try to see, okay, then probably I can prove it. So I try to I give a proof. And then I have several bad events you have to consider, different type of events you have to consider. And then we see that some bad events looks very hard to control. It may be possible to happen. Then I try to see whether that bad event can be used for the attack. Okay, then I come back to, I'm down becoming the attacking mode. Then try to use that bad event and then try to see whether attack is possible. Then I say, okay, no, attack is not possible because this bad event is not required. Probably a weaker bad event will be enough. Okay, so then I come back to the security point. Again, so this to and fro movement I do. Like so I do not know whether at the end I will write a proof paper or the attack paper. So this type of approach, and at some point of time I converge, and then either it's proof or attack. I have a result. Whatever it is a result. Okay.
Thank you very much. Nice answer, Mridul.
Yes.
One more question we have here. Can we have advice about books and references to read about indifferentiability?
Books, I don't know. For indefensibility, I don't think any books consider these notions. Papers, you can actually, the moral paper will be a little more difficult to follow because this is the first paper, 2004 paper. But definitely you should read once after you get certain idea about the indefensibility. But there is one more paper by Coron. That paper you can read, the Coron et al. I can give that reference to one of you, and then you can circulate that. The Coron et al. Coron, and there are other authors actually. I don't remember all of the name. Coron, Dodis, and there are two more authors. So there is a paper on indefensibility, on market-damgard, and other hash functions. Okay, so that's a security, that proof attack. Sorry, proof paper. Like they have given proof for not for the market-damgard actually, a variant of the market-damgard. Okay, so market-damgard is not indefensible because of length-station attack, but there are some variants of the market-damgard. Those are actually indefensible. Okay, so that paper actually talks about this. So maybe you can see that paper. I think that is a starting point. I also read that paper in the beginning. So
okay, thank you very much.
Yeah, the Coron et al. Market-damgard indefensibility. If you Google it, possibly you get that paper. Otherwise, I can give the link.
Okay, thank you very much. Unfortunately, we are running out of time, but I would like to ask you a final question before let you go. Can you share some words about how is it going? What's your view about the round 3 NIST lightweight contest? Any?
Yeah, so right now we have a, what you exactly want to know, like what is status of that, or?
Yeah, the status, if you would dare to make some predictions.
Oh, so basically right now that the 10 candidates are the finalists. Okay, and what I believe that NIST is going to take 2 candidates out of these 10. NIST can choose 0, 1, or 2, but I have a strong belief that NIST will choose 2 candidates. One will be like the hardware friendly, and the other one will be like IoT friendly, like a little bit software oriented friendly. So these 2 candidates will be like a portfolio, like 1 and 2. And my guess will be like it should be from the block cipher based design. One is from block cipher, and another will be like from permutations. Okay, so that's my guess. And I already have a two candidates in the final list out of 10 candidates. And fortunately, one is block cipher, one is permutation. But it's very, very hard to get into the final 2 candidates, because they're at the end. The committee in the NIST, they will decide, because they all are like they can choose anyone. Now it's like a lucky draw to me. Or kind of some politics might happening. Maybe some people try to push, and the lucky draw, because all 10 are good. And definitely one factor is important, the performance. Now the performance things will come into the picture. But again, this performance is actually like a pushing some designs. Means because I don't have good team to push my designs, maybe some other ones has. If I spend some good effort to have a better design, better implementation, then my performance will be better. It's just like who will give a better better time or better effort for implementing that. So if they have a common designers, independent of all the designers, a common people, I think they're doing that, like trying to implement all of them fair manner, then probably get a better pictures. Otherwise, it will be like a pushing one designs by themselves. But it's very hard to tell like which 2 will be the out of 10 will be the winner. It's very, very hard to tell. But one should be block cipher, one should be permutation. That's my guess.